This section discusses hypothesis tests for one population mean when the population standard deviation sigma is known. One mean z-test is used to compare the population mean with a given constant mu0. We assume that the data is a simple random sample. The population distribution is normal, and the population standard deviation is known. The assumption of a simple random sample makes sure that the observations are independent of each other. The normality assumption can be weakened if the sample size is large. Notice that the mathematical justification lies in that the distribution of the sample mean x bar is normal. If the sample size is large, the sample mean x bar always approximately follows a normal distribution no matter what the population distribution is. This is guaranteed by the central limit theorem. The assumption of known sigma is not realistic in practice. We will discuss more realistic case with an unknown sigma later. Follow the steps below to perform a hypothesis test for a population mean mu. First, correctly identify the null and alternative hypothesis. The null hypothesis is always mu equals mu0. There are three different possible alternative hypotheses, namely two-tailed test mu not equal to mu0, left-tailed test mu less than mu0, and right-tailed test mu greater than mu0. Which alternative hypothesis to use in practice is determined case by case in applications. It is usually the statement we want to find evidence for. After that, we need to decide on the significance level alpha. This choice of alpha is a convention. Most disciplines use alpha equals 0.05. Occasionally, some may use alpha equals 0.1 or 0.01. Then compute the test statistic. It is the z-score of the sample mean x bar. Use x bar minus mu0 and divided by sigma over square root n. Notice that no matter which alternative hypothesis we use, we compute the test statistic in the same way. We usually denote the test statistic as z0. There are two different ways to draw a conclusion about the hypothesis, namely critic value approach and the p-value approach. For the critic value approach, we need to find critic values. According to which alternative hypothesis we choose, we find critic values in different ways. Recall that these critic values are boundary values for the rejection region. If the test statistic z0 falls in the rejection region, we reject H0. Otherwise, do not reject H0. For a two-sided test, the critic value is plus minus z alpha over 2. The rejection region contains two parts, either smaller than negative z alpha over 2 or larger than z alpha over 2. For a left-tailed test, the critic value is negative z alpha. The rejection region is less than negative z alpha. For a right-tailed test, the critic value is z alpha. The rejection region is larger than z alpha. These critic values can be found using standard normal table. Pay attention to the two-tailed test, because the rejection region contains two parts, either with probability alpha over 2. The critic values are plus minus z alpha over 2, but not z alpha. We can also draw a conclusion to the hypothesis test using the p-value approach. How to compute the p-value depends on which alternative hypothesis to use. For a two-tailed test, the p-value is the sum of two probabilities, larger than the absolute value of z0 or smaller than minus absolute value of z0. Because of symmetry, the probability of these two parts are equal. We can calculate the probability of one of them and then multiply it by 2. For a left-tailed test, the p-value is the probability less than z0. For a right-tailed test, the p-value is the probability larger than z0. We can see that the p-value for two-tailed test is double of the p-value for one-sided test. Therefore, it is important to choose the correct alternative hypothesis in applications. After the p-value is computed, we compare the p-value with the significance level alpha. If the p-value is less than or equal to alpha, reject H0. Otherwise, do not reject H0. No matter whether we are using the critical value approach or p-value approach, make sure to interpret the results of the hypothesis test. We have mentioned that the hypothesis is exact for normal distribution. When the population is not normal, it is approximately correct, which is guaranteed by the central limit theorem. Let's make some comments on when to use the one-mean z-test. We had similar comments when we discussed how to construct confidence intervals for population mean. When the sample size is small, less than 15, the z-test should be used only when the variable under consideration is normally distributed or very close to being so. We can check the normality assumption using a normal probability plot. When the sample size is moderate, between 15 and 30, the z-test can be used unless the data contain outliers or the variable under consideration is far from being normally distributed. When the sample size is larger than 30, the z-test can be used essentially without restriction. The main idea of this discussion is the trade-off between normality assumption and the sample size. If the sample size is large, we do not need to worry too much about the normality assumption because the central limit theorem kicks in. If the sample size is not very large, we need to make sure that the population distribution is close to normal. Outliers always cause issues to one-mean z-test. The test statistic is based on the sample mean. We know that the sample mean is not robust to outliers. Therefore, one-mean z-test is also not robust to outliers. We can identify outliers from normal probability plots or box plots. Notice that an outlier means an observation that is far away from the remaining data. Sometimes outliers mean recording errors. Try to correct them or simply remove them. If outliers are present but their removal is justified and results in a dataset for which the z-test is appropriate, as previously stated, the procedure can be used. If outliers are present and their removal is not justified, you should perform the hypothesis test once with the outliers and once without them to see what effect the outliers have. It means that we try to conduct hypothesis testing twice. For the first one, we use all data. For the second one, we remove the outliers and then conduct hypothesis testing. We will check whether the results are consistent. If yes, leave the outliers in the data because it does not cause any trouble. If the two hypothesis testing yield different conclusions, the outlier affects the result of analysis. If it happens, we may need to take another sample or try to use a different procedure. There are some procedures which are robust to outliers. The textbook also discusses some. For example, Wilcoxon tests. However, we will not discuss them in this course. You may read them if you are interested. Let's look at one example. A half-century ago, the average US woman in their 20s was 62.6 inches tall. The height in inches of a random sample of 25 of today's women in their 20s is presented in the slides. At the 1% significance level, do the data provide sufficient evidence to conclude that the mean height of today's women in their 20s is greater than the mean height of women in their 20s a half century ago? Assume that the population standard deviation of heights for today's women in their 20s is 2.88 inches. The problem asks us to compare the population mean height of women to a fixed number, 62.6 inches. The population standard deviation is known to be 2.88. The sample size is n equals 25. It is moderate. Therefore, we need to check the normality assumption. The normal probability plot is shown on the slide. We can see that points roughly fall on a straight line. The distribution is normal. We can use one-mean z-test. According to the problem, it is suspected that the mean height of women is larger than 62.6 inches. The problem asks us whether the data provide evidence to this statement. Therefore, the alternative hypothesis is right-tailed, mu larger than 62.6. The null hypothesis is mu equals 62.6. The significance level alpha is 0.01. We can compute the test statistic as follows. Z0 equals x bar minus mu divided by sigma over square root n. Here, x bar is the sample mean, sigma is the population standard deviation, and n is the sample size. We can compute the test statistic as 2.85. We can continue using the critical value approach or p-value approach. Using the critical value approach, we need to find the critical values. Notice that there are different ways to find critical values. This problem is right-tailed, and the critical value lies in the right tail of the normal curve. Because the significance level alpha equals 0.01, the critical value is selected such that the probability to the right of this value is 0.01. Using the standard normal table, we can find the critical value is z 0.01 or 2.33. The rejection region is thus the area to the right of 2.33. Compare the test statistic with 2.33. The test statistic is larger than 2.33. It falls in the rejection region. Therefore, we reject H0. We can also use the p-value approach. The p-value for a right-tailed test is the probability to the right of the test statistic. The test statistic is 2.85. We need to find the probability to the right of 2.85. Using the standard normal table, we can find that the p-value is 0.0022. Notice that the standard normal table only shows the probability to the left of a value. After finding the probability corresponding to 2.85 in the standard normal table, we need to subtract it from 1 to get the probability to the right of 2.85. Compare the p-value with the significance level 0.01. It is smaller than 0.01. Therefore, we reject H0. No matter which approach you use, it leads to the same conclusion, rejecting H0. Therefore, at the 1% significance level, the data provide sufficient evidence to conclude that the mean height of today's women in their 20s is greater than the mean height of women in their 20s a half century ago. A simple random sample of 18 adults with incomes below the poverty level gives the daily calcium intakes shown in the slide. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean calcium intake of all adults with incomes below the poverty level is less than the RAI of 1000 milligrams. Assume that the population standard deviation sigma equals 188 milligrams. This is also a one-mean z-test problem. The population mean is the mean daily calcium intake. We want to compare the mean daily calcium intake with 1000 milligrams, which is the recommended adequate intake. The population standard deviation is given. The sample size is n equals 18. It is moderate. We need to check the normality assumption. The normal probability plot is shown on the slide. All points roughly fall on a straight line. Therefore, the normal assumption is satisfied. We can assume that population distribution is normal. The null-hypothesis is mu equals 1000. The alternative hypothesis is mu less than 1000. Notice that the problem specifically asks, do the data provide sufficient evidence to conclude that the mean calcium intake is less than 1000 for adults with incomes below the poverty level? It is suspected that they do not take enough nutrition. The word less than gives us a hint that we should use a left-tailed test. The significance level is 0.05. We compute the test statistic as follows. Z0 equals x bar minus mu0 divided by sigma over square root n. Here, x bar is the sample mean, mu0 is the value in the null-hypothesis, sigma is the population standard deviation, and n is the sample size. The test statistic is therefore negative 1.19. We can either use a critical value approach or p-value approach. Using the critical value approach, we need to find the critical value because the alternative hypothesis is left-tailed. The critical value is at the left tail of the normal curve. We select the critical value such that the probability to the left of it is 0.05. According to the standard normal table, the critical value is negative 1.645. The rejection region is the area to the left of this value. Compare the test statistic with this value. The test statistic is negative 1.19, which is larger. Therefore, the test statistic falls outside of the rejection region. We do not reject H0. Using the p-value approach, we need to compute the p-value. For a left-tailed test, the p-value is the probability less than the test statistic. Using the standard normal table, the probability less than minus 1.19 is 0.1170. The p-value is larger than the significance level 0.05. Therefore, we do not reject H0. Both approaches conclude that we do not reject H0. Therefore, at the 5% significance level, the data do not provide sufficient evidence to conclude that the mean calcium intake of all adults with incomes below the poverty level is less than the recommended adequate intake of 1000 milligrams per day. This example discusses cheetahs. One common estimate of mean top speed for cheetahs is 60 miles per hour. The data contain the top speeds in miles per hour for a sample of 35 cheetahs. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean top speed of all cheetahs differs from 60 miles per hour? Assume that the population standard deviation of top speed is 3.2 miles per hour. Because the population standard deviation is known, this is a one-mean z-test problem. The sample is 35 and it is large. We may not need to worry about the normality assumption, but we still need to check outliers. The slide shows the normal probability plot and the box plot. From the normal probability plot, we can clearly observe one outlier, which is also confirmed by the box plot. In practice, in order to check outliers, you do not need to draw both plots. Usually, the box plot is enough. Because there is an outlier, we will try to conduct the one mean z-test twice. First time, use all data. Second time, remove the outlier. The null hypothesis is mu equals 60 miles per hour. For the alternative hypothesis, because we have no idea whether the mean speed is larger than or smaller than 60, we choose a two-sided test. Therefore, the alternative hypothesis is mu not equal to 60. The significance level is alpha equals 0.05. We can compute the test statistic as follows. Notice that it is computed using all data. The sample size is 35. Z0 equals x bar minus mu0 divided by sigma over square root n. Here, x bar is the sample mean, mu0 is the value in the null hypothesis. Sigma is the population standard deviation, and n is the sample size. After calculation, the test statistic is Z0 equals negative 0.88. We can use either the critical value approach or p-value approach. Using the critical value approach, we need to find critical values. Notice that for a two-tailed test, there are two critical values, which are on both tails. They are 1.96 and negative 1.96. The rejection region is larger than 1.96 or smaller than negative 1.96. The test statistic is negative 0.88, which does not fall inside of the rejection region. Therefore, we do not reject H0. Using the p-value approach, we calculate p-values. For a two-tailed test, the p-value is the probability of two parts. Because of symmetry, we can compute the probability for one part and then multiply it by 2. The p-value is 0.3788, which is much larger than 0.05, the significance level. Therefore, we do not reject H0. Both approaches conclude that we do not reject H0. At the 5% significance level, the unabridged data do not provide sufficient evidence to conclude that the mean top speed of all cheetahs differs from 60 miles per hour. We can remove the outlier and repeat the procedure. Because one outlier is removed, the sample size becomes 34, and the sample mean is 59.062. Compute the test statistic in the same way. It is negative 1.71. We can see that this test statistic is smaller than the previous test statistic with all data. If using the critical value approach, the critical value is plus minus 1.96. The test statistic does not fall in the rejection region. We do not reject H0. If using the p-value approach, the p-value is 0.0872. Although this p-value is smaller than the previous p-value, it is still larger than the significance level 0.05. Therefore, we do not reject H0. As a conclusion, at the 5% significance level, the abridged data do not provide sufficient evidence to conclude that the mean top speed of all cheetahs differs from 60 miles per hour. Therefore, we can see that removing the outlier does not affect the conclusion of this hypothesis test. Notice that although in this example the outlier does not affect the conclusion of the hypothesis test, it is possible that in other examples, outliers may affect the conclusion of the hypothesis. In practice, whenever there exists an outlier, we need to be careful. We need to distinguish between statistical significance and practical difference. If the null hypothesis is rejected, the result is statistically significant. However, it does not necessarily mean that the difference is important in any practical sense. For example, the manufacturer of a new car claims that a typical car gets 26 miles per gallon. We suspect about this claim and want to test mu equals 26 against mu less than 26. Here, mu equals the population mean miles per gallon of the car. Suppose we take a sample of size 1000. The sample mean is 25.9 miles per gallon. The test may be significant at level 0.05. However, from a practical point of view, no one will care about the difference of 0.1 miles per gallon. The difference between 25.9 miles per gallon and 26 miles per gallon is not important. Although the difference is statistically significant, the difference is not practically significant. Last, we want to draw a connection between hypothesis test and the confidence interval. For two-tailed hypothesis test for a population mean at significance level alpha, H0 will be rejected if and only if the value mu0 given for the mean in H0 lies outside the 1 minus alpha level confidence interval for mu. Let's use a concrete example to explain what I mean here. For the cheetah example, a 95% confidence interval for the mean top speed is 58.5 to 60.6. If we want to test H0 mu equals 60, because this confidence interval contains 60, we do not reject H0. If we want to test a different hypothesis, for example, H0 is mu equals 65, because this confidence interval does not contain this value, we reject H0. When using this connection, we need to pay attention to two issues. Firstly, alpha should match. A 95% confidence interval corresponds to significance level 0.05. Secondly, the test must be two-tailed.